Okay, thank you very much. So first of all, I'd like to thank the organizers, especially Koushik, for all the efforts in organizing this wonderful workshop. And I will talk about this Axion dark matter, and this is partly based on the work in collaboration with Masaki Yamada and Wen In. Uh, okay, so this is outline of my talk. After giving a very short and incomplete review of a possible explanation of XENON1T excess, I will focus on one of viable scenarios, namely the Axion dark matter. Then I will summarize my talk. So as many of you might have heard before, the XENON1T collaboration recently reported uh, an excess of electron recoil events around a few kV region. And this excess might be due to tritium, but it could be due to some physics beyond the standard model. And some possible interpretation were already examined in the XENON1T paper, and many interesting ideas have been proposed so far. But anyway, all those models must explain the following 2 points. So namely, to explain the excess around the KV, some particle, say, must sneak into the XENON1T detector and somehow gives an energy over the KV to either electron or photons. And also, the number of events and the spectral shape must be explained. So these are very important constraints on the models. And for instance, if the predicted spectrum were too soft, it would not give a very good fit to the data. Okay? So looking a bit more closely, all those models can be classified by considering how they explain the following. So first, what is the particle? Okay, what is the origin of this particle? What's the mass? What's the spin? Or does it play any cosmological role? And actually, in some scenarios, it is related to dark matter. In others, it is not. And what is the interaction? Namely, how does the particle induce the electronic recoil event? So depending on the interaction, it may give an energy to electron or photon, or it may be absorbed by electron, or it may scatter off the electron. It is also very important to satisfy various bounds coming from, for instance, stellar cooling argument, the other direct or indirect dark matter search experiments, BBN, structure formation, and so on and so forth. This is, of course, model dependent, but if your model does not satisfy any of the bounds, you have to either give up the model or extend it to make it satisfy all the bounds. And furthermore, if your model can explain the energy over the KV and also the required strength of the interaction, so your model is very attractive because you can answer the why KV, why this much excess type questions. It will be also even better if your model has testable prediction within the reach of future experiments or observations. Okay. So the origin of the particle might be related to dark matter or maybe totally unrelated to dark matter. So in the former case, this particle, so let us call it chi, may be dark matter itself, or it may be created by annihilation or decay of dark matter. So in this case, the produced chi particle can have relatively large velocity, and which is actually advantageous to explaining the XENON1T excess, as I explain on the next slide. On the other hand, this particle chi may be totally unrelated to dark matter, but simply it exists and it has coupling to the standard model particles. It may be created inside the sun and propagate to us. The examples include solar axion, solar dark photon, or solar neutrino with exotic interaction. So let us focus on the case where this particle chi has an interaction with electrons. So in this case, we still have two ways to give an energy to electrons. One is absorption, the other is scattering. So in the case of absorption, the energy of chi becomes the recoil energy of electron because chi particle is absorbed by electron. And if chi is non-relativistic, its mass must be over the keV to explain the electron recoil events around kV. And if it is relativistic, its kinetic energy must be over the kV. And if chi particle is produced from the sun, its highest energy, which may not be typical energy, that depends on the model, but highest energy can be naturally over the kV. So in that case, you may be able to explain the kV energy naturally. I will focus on the case of absorption later, so only a few words about the case of scattering. So in this case, especially in the case of simple elastic scattering, namely the same chi particle appears both in the initial state and the final state, it is very hard to give an energy over the kV to electron through scattering, because the recoil energy can be estimated by transferred momentum squared, so mu is the reduced mass, v is the relative velocity, over the electron mass. So this is bounded above the electron mass times the v squared. So in order to give an energy over the kV, the velocity of this chi particle must be very high. So velocity should be faster, than about 10 times the speed of light, which is much faster than the galactic escape velocity, about 0.002 times the speed of light. So in this case, we certainly need an acceleration mechanism or production mechanism to generate chi particle with such high velocity. And many interesting ideas have been proposed so far. Also, it is very important to satisfy other bounds. For instance, bounds coming from the stellar cooling argument based on the evolution of the sun, or white dwarf, red giants, horizontal branch stars. And this chi particle may not be completely stable, but decay into lighter particles, such as a pair of photons. In this case, there's very tight bound coming from the X-ray observations. There are also other limits coming from BBN, structure formation, and so on and so forth. And so far, many interesting ideas have been proposed. You can find all of them on arXiv, but it is far beyond my ability to explain all of them. So I will focus on the Axion dark matter in the rest of my time. Okay. So here, ALP stands for axion-like particle. So this is a general pseudoscalar particle, and not necessarily the QCD axion. So axion or axion-like particle is known to be a viable candidate for dark matter. And there are two important parameters. One is mass, MA, the other is decay constant, FA. FA gives us a characteristic scale in the free space of the axion. In the simplest case, the decay constant FA is directly related to the periodicity of the axion potential. And it also determines the strength of interaction with standard model particles. For instance, the axion photon coupling, here if mu nu is the free strength of U1 electromagnetism, and the coefficient is Ga gamma gamma or Ga gamma, which is mass dimension -1. So it is inversely proportional to the decay constant FA. And it is also generally coupled to fermions, including electrons. And here, Ce is a PQ charge of electron. And if you go to another basis, so by performing field-dependent chiral rotation with axion, so electron, at the leading order, you have this interaction, axion coupled to psi, this electron field, by gamma 5 psi e, and the coefficient is given by GAE. This is a dimensionless coupling, and related to the PQ charge of electron, C times electron mass and over FA, like this. And such an axion or axion-like particle dark matter has been searched for by many experiments. And recently, a XENON1T experiment placed a very stringent limit from kV mass to 200 kV here, sorry. And as you can see, the bound they actually obtained around a few kV region is significantly weaker than expected. That is shown by this green and yellow bands. And so this is, of course, due to the excess they found. And they analyzed data by assuming the monoenergetic peak, which is expected in the case of absorption of bosonic dark matter, and found that the axion mass around 2.3 keV and axion electron coupling are equal to a few times 10 to minus 14 are favored over the background, and the statistical significance is about 3 sigma, including the looking elsewhere effect. So the question I'd like to ask here is, can we really have a viable axion or axion-like particle dark matter with these properties? Namely, mass is around keV, and the GAE, the axion electron coupling, is about 10 to minus 14. And in addition to electron, such an axion is generically coupled to photons. So if you consider this triangle diagram where the charged fermions coupled to axion are running in the loop, you generically obtain the anomalous coupling of axion to photons. And we have various contributions coming from fermions running in the loop. And assuming there's no cancellation among those contributions, we expect the coupling of axion to photon GA gamma is about the fine structure constant alpha times PQ charge, say CE, over FA. And in terms of the axion electron coupling, by using this relation, we can express it in like this, so alpha GAE over ME. And because we know the suggested mass and decay constant from the XENON1T excess, we can estimate the partial decay rate of the axion to 2 photons. It is about 10 to 21 seconds for those suggested values of mass and coupling. But there's very tight constraint coming from the X-ray observations, and it requires a lifetime to be longer than about 10 to 28 seconds. Okay. So there's about 7 orders of magnitude difference here. And of course, we are not the first to point this out, and it has been known for a while. For instance, please look at this paper. But anyway, we have to suppress the axion photon coupling to satisfy this X-ray bound. And so this motivated us to consider the so-called anomaly-free ALP dark matter, where the axion photon couplings are canceled out. So we have various contributions from different fermions, but PQ charges assignment are such that those contributions are canceled out. Okay. Then we can suppress axion photon coupling, and we can satisfy the X-ray bound. However, we still have non-zero coupling between axion and photons because of the threshold corrections. So for the parameters we are interested in, the electron and the muon, those charged fermions are heavier than axion mass, so we can simply integrate them out. Then, by assumption, this anomalous contribution vanishes. However, we still have finite threshold corrections, and they are suppressed by the fermion mass like this, me squared and mu squared if axion is coupled to muon, and so on. And generically, these threshold corrections are dominated by that of electron, simply because electron is the lightest charged fermion in the standard model. Then, because we are interested in the decay of the axion to real photons, so we impose the on-shell condition on the axion and the photons. We arrive at the effect operator between connecting between axion and photons like this. So compared to the previous anomalous coupling, it is now suppressed by the mass squared ratio, MA squared over ME squared. So this is KV, this is 511 KV. So from here, we have about 4 orders of magnitude suppression. So this is sufficient to avoid the very tight X-ray bound. But it does not only avoid X-ray bound, it also predicts an X-ray line with a definite strength, because this threshold correction is dominated by electron, and this fact is universal for various realizations of the anomaly-free ALP dark matter. And it is the partial decay rate is proportional to the axion mass to the 7th power. Okay. So you might not be familiar with this peculiar dependence, but actually this result is very similar to the naively estimated decay rate of neutral pions before the discovery of anomaly. Okay. So this is the concrete conditions for the anomaly-free ALP dark matter. So the electromagnetic anomaly as well as color anomaly should vanish. So the latter is because we want to avoid mixing with pions. So there are various realizations, for instance, leptophilic ALP dark matter, in which the axion is coupled to only electron muon or electron tau, or there's also a DFSZ-like realization based on a 2x doublet model. Anyway, a general UV model is such that there is a basis where the axion couplings are expressed by or in terms of derivative coupling like this, and there's no anomaly. So such an, in other words, this anomaly-free ALP dark matter is such that the shift symmetry of the axion is completely preserved in the interaction with standard model particles. And such an axion particle can be produced various ways. So probably you learned from the Dodi's lecture. For instance, axion particle can be produced by the misalignment mechanism. And in the other universe, there's no strong reason to expect the axion to sit exactly at the low energy minimum. And it is expected to be generically deviated from the minimum by some amount. So this theta star is the initial misalignment angle, which is expected to be over the unity. And then by using the decay constant around 10 to 10th GeV, suggested by the XENON1T excess, you can explain the whole dark matter by the axion produced by the misalignment mechanism if the reheating temperature is higher than about 10 to 6 GeV. Namely, if the reheating is completed before the axion starts oscillate. Okay. In that case, axion produced by this mechanism can explain all dark matter naturally. So you don't need any fine-tuning of the parameters in this case. On the other hand, if the reheating temperature is lower than 10 to 6 GeV for some reason, then the abundance of the axion produced by this mechanism is too small to explain all dark matter. So in that case, we need to invoke the clockwork mechanism, for instance, clockwork mechanism to enhance this contribution, or we may have to make use of the an harmonic effect, namely the axion may be sitting around the top of the potential. Another production mechanism is the thermal scattering. So if the reheat temperature is higher, and if the axion is coupled to heavier fermions, this thermal production is more efficient. And so its abundance is given by this expression. So in terms of reheat temperature, as well as coupling to heavy fermions. But because the mass of the axionic particle is around kV, if they are produced thermally, so they cannot be cold dark matter, but warm dark matter. And there's an upper bound on the fraction of warm dark matter from the observations. And it can be at most about 10% of total dark matter density. So if the axion is coupled to heavy fermions like top quark or bottom quark, then in order to avoid or even satisfy the warm dark matter bound, the reheating temperature cannot be very high. So it should be as low as, say, the weak scale or so. On the other hand, if the axionic particle is coupled to only electron and muon, then the reheating temperature can be as high as 10 to 8 GeV without running afoul of this warm dark matter bound. Okay. So in this case, for the reheating temperature between 10 to 6 GeV and 10 to 8 GeV, you can explain all dark matter by the axionic particle produced by the misalignment mechanism. So this is our result. So this axion mass and the axion electrocoupling. And this star represents the region preferred by the XENON1T excess. And this shaded region, blue shaded region, are excluded by the X-ray observation. And as you can see, this preferred region is well below the current bound, thanks to the anomaly-free nature. And this X-ray bound will be improved down to this blue dashed line by the future X-ray observatory, such as Athena. And this gray region is excluded by the argument based on the stellar cooling argument, namely red giant and white dwarf. And slightly below this excluded region, there is a region favored by the cooling argument of white dwarf and the red giant. Although this is not statistically significant, but there is some parameter space which is favored by this argument, cooling argument. So this region preferred by XENON1T XS is below the this cooling anomaly. Okay. But if you consider a case where the axion occupies only fraction of dark matter, as in the case of axion produced by thermal scattering, then simply because we have less amount of axion, we need to have larger axion electron coupling to explain the same number of events observed by the XENON1T experiment. So the axion electron coupling becomes larger, so we have a better agreement between the star cooling hint and the XENON1T result. Okay. By the way, this X-ray band also goes up, but the stellar cooling argument does stay there because this argument does not depend on the abundance of the axion. And this one does depend on the abundance of axion. Okay. So lastly, let me briefly mention an interesting coincidence, namely the XENON1T XS prefers a particular choice of parameters, namely the mass is around kb and FA is around 10 to 9 or 10 to 10 GeV, and why is that? So actually, this parameter is consistent with predicted relation between mass and decay constant by the ALP inflation model. So Axion is also a good candidate for inflaton because the shift symmetry can protect the potential from receiving large radiative correction. But the simple cosine term does not give us viable solar inflation model because potential is not very sufficient flat as long as decay constant is smaller than Planck scale. But any periodic potential can be expanded in terms of Fourier series. So some of many cosine functions, cosine phi and cosine 2 phi and so on. So if those some of the cosine terms, say 2 of them dominate potential and conspire to make a potential very flat around the top of the potential, then you can have hilltop type inflation model from the axion-like particle with 2 cosine terms. Then you have, due to limited time, I can explain, but we can derive a consistency relation between decay constant and mass like this, solely from the CMB normalization of density perturbation. And actually, interestingly, the suggested parameters have an overlap with this predicted consistent relation like this. Okay. So let me wrap up my talk. So many interesting ideas have been proposed to explain the XENON1T XS, and they can be classified according to these points. And here I focus on the one of such viable scenarios, namely anomaly-free axion dark matter. And thanks to this anomaly-free nature, it has a very suppressed coupling to photons. And it does predict an X-ray line with a different strength because threshold correction is always dominated by electrons. And this suggested electron coupling satisfies the stellar cooling bound. And also, interestingly, it may be that axion-like particle explain both dark matter and inflaton. Okay, that's all. Thank you very much for your attention.
Thank you, Fumi. There's a question in the chat from Shahari, who asks, what is meant by threshold correction?
Because the cancellation is not exact because we can integrate those fermions, but there's mass-dependent correction. Okay, and in this case, if you integrate the electron, for instance, okay, we are left with this anomalous contribution, anomalous coupling, as well as this effective operator connecting axion and photons like this. And what is important here, it does depend on the fermion mass. And because, so if, for instance, if it's coupled to electron muon, and if the mass of electron and muon are equal, then we would have no interaction between axion and photons in the low energy. But in the actual world, the electron mass and muon mass are different. So even if we have anomaly cancellation between the two, we do have some finite correction. Does it answer your question? We have another.
Yeah, there's another question, and it's actually the same question I was going to ask.
Okay.
So I'll say this: in the axion reflection, when you have this dark matter candidate also being the inflaton, is it a scenario where the inflaton doesn't completely decay, and is the dark matter a remnant of the inflaton? So yeah, and I have the same question. How does reheating basically happen in this case?
Actually, for the parameters of our interest, if decay constant is relatively small in the context of reheating, so actually, if you calculate the decay rate and also the evaporation rate, the axion or axionic particle decay and evaporate within the Hubble time. So it is instantaneous reheating. But in this process, axion is also thermalized, and this thermalized axion contribute to warm dark matter. So it can be as large as 10% of total dark matter density. So in this case, we cannot explain whole dark matter, but only 10% of dark matter.
So if I can like rephrase that answer, so the condensate, the field that's doing inflation decays, but then the reheat temperature is high enough that you then thermally produce the particles as well. Okay.
So the mass at the potential minimum is very small. So that's why the axion is stable. But when it oscillates with a large amplitude, it feeds effective mass, which is much higher. So it can decay perturbatively to electron with a short time scale. And then they are thermalized, and the axion has interaction with those plasma. So then sooner or later, this condensate will evaporate in one Hubble time.
Mm-hmm. Okay, great, thanks. Okay, so I don't see any more questions, and we're just out of time. So thanks again to Fumi.
Okay, thank you very much.